to B to C, what is epsilon doing, going from here to here? Decreasing. Then at B, it's starting to increasing. Okay? And what is this axis here? It's alpha. Alpha determine how far you went. So this says the epsilon, the alpha, the place we want to find is when the slope is 0 along that direction. Okay? So you just simply take a derivative with respect to alpha, and of course this is just that, and this is that. You set it equal to 0 to find out the correct alpha, and you rearrange this, and you just go through that, and you see that when you rearrange this, you get a specific formula for the step length. Do you know delta x, Lookman? He's now writing his step length subroutine. Abdullah, do you know delta x?
How far?
Now delta x is a gradient vector, right?
Yeah.
It's this direction. You already computed the gradient, right? So delta x is a negative gradient.
Yeah.
You know that?
I know that.
Do you know this? Well, that's what delta x is. Do you know this? Yes.
Yeah.
Do you know h? It's L
H.
transpose L. So you know all these entities. Just plug them into your subroutine. In fact, next time he's going to actually not only show it as a MATLAB code, but he's going to actually show us a code for computing that for his subroutine step, and that gives you the alpha. Okay, and you recognize this as a gradient direction, so you just put gradient. Actually, this is the negative 8 gradient direction, so the negative gradient is delta x equals negative gradient, so the negatives cancel. Got it?
Yeah.
Scale of 1 to 10?
10.
Lookman, you've never had an optimization theory course, I can tell.
No.
Okay, well, now you're getting your crash course, and that will be done after today. Okay, what's the problem with this step length procedure? Marco?
The
H.
the conditioning.
No, it's well conditioned. It's okay conditioned. Not great, but what's the problem with this?
It is looking for.
Do you really trust math, Marco? No, I don't trust it. What are the assumptions being made here?
L'alfa è small, famiglia, infinitesima.
Well, one of the assumptions is whatever h was over here is the same h as over here. And that's going to be true when what? When what?
When the linear function.
It's a linear, our original problem was linear. But if it's non-linear, like we generalized the Rosenbrock function, that ain't going to be true. So this is going to be a bogus step length. So if you just have a linear, overdetermined system of equations you want to solve for, this isn't too bad. Precondition will help you out. But definitely if you do a nonlinear system, trying to solve a nonlinear system of equations with this, forget it. You want to get much more help in finding that step length. But this is at least get you started in understanding step length. So if you have a nonlinear system of equations like this, a Rosenbrock function, we already talked about that. Right? I talked about the Rosenbrock function. Someone tried to correct me. But anyway, notice here you have a very different curvature than the matrix than you have here. Things change very much differently. So what you have to do is abandon this analytical step length formula and go through a step length formula. And I'm not going to go through that carefully. That's something you guys need to do. I can't hold your hand all the time. But you basically, what you do is you, say you're right here. And you need to go somehow in this direction, right? Because it's not your gradient. You don't trust the step length formula. By the way, this is a low right here. This is a valley. This is the Po Valley. Over here, it's surrounded by what mountain chain is it? Po Valley. What mountain chain is surrounding it? What?
Mountain chain.
Yeah, what's the name of the mountain chain surrounding the Po Valley? Po. The Po Valley is in Italy, right?
Ah, the Po Valley.
Yeah,
okay.
the Po Valley.
I was thinking you were thinking the Alps.
Okay, the Tian Shan Mountains. What valley is beneath the Tian Shan Mountains?
Pianura Padana.
Li. Oh, Li, yeah. What's the valley beneath the Tian Shan Mountains?
I don't know.
Sure you?
I could recall.
I have the answer for the Italian side. Pianura Padana.
Okay, whatever you said. Whatever you said, mountains, and then this is the Po Valley, okay? So the gradient is kind of pointing in the right direction, but you don't trust the previous formula. Why, Marco or Abdullah?
Because H is
Yeah, this is not a linear.
Linear.
This doesn't look like the ellipses I talked about, because the curvatures are changing all over the place, and with a linear system of equations, curvature should be constant. Period. What's a quick and dirty proof of that, Marco? For a linear set of equations, it gives rise to a quadratic misfit, right?
yes.
If you take a derivative twice, do you have anything in a function of x?
No.
No, it's constant. Okay, that's a quick proof. So, what you do is you move along this direction, and what you do is you select 2 points ahead of it, here and here. And then with these 3 points, 1, 2, 3, you fit a quadratic polynomial along that direction. And with a quadratic polynomial, you can figure out where the low point is. And that's what this is. I'm not going to go through that. What's the problem with this approach? The problem with this approach is you got to find a point not only downhill, but the third point has to be uphill. Right? Because as you go down, you want to come back up again. So you got to have an uphill point, a downhill point. Let me draw what I just said. Here's my starting point. Look, man. Now let's say we're really stupid. I picked 2 points ahead of this guy. Tell me where to pick. Look, man. Okay. And okay, so we're really stupid now. Okay. So I now have a polynomial, a quadratic polynomial. I'm going to fit the value of the epsilon here. I already know the epsilon there. I got to now find, it's going to be a polynomial that'll be epsilon. Okay. What was that? A plus B alpha plus C alpha squared. Okay. So there's some polynomial curve in alpha that I'm going to fit to here. And then there's a way to figure out what the A, B, and C are from the values of epsilon at this 1 point and 2 point. If I know these two values of epsilon and this value, I can figure out the 3 unknowns A, B, C that fit a quadratic to this curve. Does the slope go to 0 between here? Look, but no. So we were stupid. Why were we stupid? We deliberately were stupid because we chose 2 trial points that did not fulfill my criteria. One has to be downhill, and that one's downhill, but the other one has to be uphill. Okay, and then when you do that, then this kind of thing will have a solution, and hopefully it's right here. Okay, so that's a general idea. I'm not going to go through the details, but you can do it. That's called a step numerical line search. The problem with that is, to get these 2 points, you have to do a whole series of forward modeling for this point of the model and this point of the model. That's kind of expensive, but still it's worth it. Okay, in summary, We looked at the nonlinear problem as opposed to the linear problem, and we had a very similar formula for preconditioned steep descent. The only difference is now the x's have a superscript in them. Because the gradients changed and the curvatures changed, depending on where we were, and that's what that means. We have to update these guys at each iteration because we're changing our position. With a linear problem, they didn't have a K up here. Geometrical meaning of the Hessian Abdullah in 7 words or less.
Okay, so basically this is
7 words? No, you already hit us with 4 words.
the curvature direction in
4.
S.
Curvature direction.
In S.
What?
In S.
Along S.
Along S.
Oh, yeah. It's not curvature direction, it's the curvature along S. It's 3 words. Okay. And of course, it varies all over the place. And a multi-scale procedure you might keep in mind. We'll talk more about that in detail, and that's similar to pool, max pool. Half the neural network story is that, but the full neural network story is when you put the squashing function there. The step length, there's many variations of step length. We'll go through that in more detail when we get to CNN, because they're very important. And the sum of the squared errors for Taylor series expansion will give you forms that look like this. A Hessian, the gradient, and this is for the linear case. We chose to call this H. And if it's truly a nonlinear problem, we can't call it just X transpose X. It's got to be different. Radius descent formula that Abdul is going to educate us next week on, not only the MATLAB code for it, but also the step length code. And there's interpretations of the gradient. When you have a linear problem, the Newton direction will directly point to the point here, and if you have a regularized steepest descent, where is that direction going to point to, Marco? You have 2 end members of the damping parameter. One is when lambda is equal to 0, lambda is equal to 0, and the other is lambda being very large. How about somewhere in between?
In between.
Point some vector in between. Okay, that's it. So, as I said before, I'm going to be leaving for a conference, and so I need a makeup class tomorrow. We're going to have a elementary Python lab Thursday. For those who don't know Python, here's your chance to catch up in 2 months. And when you know Python, then we can start doing the neural network machinery called, one of them is Keras. So who's going to attend the, because we only have a limited number of seats available for the Python lab Thursday.
What time is it?
Noon. So everyone should be available for noon. Raise your hand if you're going to attend the Python lab.
What's going to be iterative Python?
What?
What's going to be
Basic Python. You don't know anything, and he's gonna, at the end of the day, you're gonna write series descent code. What?
We package NumPy.
If you have a laptop, I would suggest you bring it there, and then we'll teach you how to load the Jupyter, what's that called? The Jupyter
Notebook?
interface. And that has all the Python codes and Keras codes you can download onto it. It's automatically downloaded.
So are you treating also Keras in installation?
We're going to use mainly Keras.
No, on
later on.
Thursday are you?
No, not Keras.
Okay.
That's too early to do Keras. But at the end of the day, you're going to be able to write your own in Python CPC code. So let me get that hand count again. 2, 3, 4, 5, 6, 7. Okay. If you already know Python, is okay. So I'll send you the coordinates by email Now, the homework is not due until Thursday. You can hand it in Thursday because Lookman was, no, not Lookman. Someone was asking for mercy. Aziz. So we're going to give Aziz mercy. So Thursday,
Thank you.
bring your homework, okay?
いつまででやるの？
What?
じゃあ、ラストに戻る。
Yeah.
No, that's it.
Tomorrow at noon, here. This for 45 minutes. I'm going to introduce the single node neural network.